Okay, so we've spoken about a variety of abstract data structures. Every time you hear that word abstract data structure, think of a data structure that is not built into iOS or to Swift, right? It's not built into Swift. Data structures that's built into Swift is arrays. You could use it as is. Dictionaries, you could use it as is. A set, we could use it as is. Those are the data structures we have in the Swift language. Okay? If you want to build any sort of data structure that's computer science related, for example, if you want to build a stack inherently, there's not a stack in Swift, right? An array behaves very similar to a stack, but if you want to stack with the push, pop similarities, right? A peak similarity there, the peak function, you have to build what's known as an abstract data structure, right? So when you think of abstract, think about something you want to build. It doesn't exist. You create it the way you want it to function, right? So far, we've built one abstract data structure. We've built the stack, right? We built the stack from the functionality of a stack. We said a stack in real world could be a stack of plates. In iOS development, we said a stack is a navigation controller, where a navigation controller pushes, right, the word push there, it pushes a new view controller onto the stack. So we take that same push functionality and we created a function called push, right? So push adds to the stack. And on our navigation controller, we could also pop. So pop is to remove from the stack, right? So we took the stack structure and we built an abstract data structure, right, using stack. We went further. We made the stack generic because now we want our stack to work with any data type, right? Whether it be an integer, a string, a boolean, our own custom type, doesn't really matter. We want our stack to work with any data type. So we saw some more concepts there. We saw abstract data structures, and we also saw generics. And generics, as we said before, it's fundamental to really build out complicated data structures. Knowing generics is fundamental. Knowing generics is paramount, right? Today, what are we building? We'll build our second abstract data structure. It's a linked list. What is a linked list? Think of a linked list like a set of trains, right? You have a set of trains, you want to add an additional car to that train, you link it to the back of the car or the back of the train cars, and you have more cars in your train, right? If you want to remove more cars, maybe you have a shorter platform, for example, the G train, right? There's short platforms in the G line. So you might want to remove some of those cars from your train, right? So picture a linked list like a set of cars on a train, right? We could add, we could remove from that train. We could add, we could remove from that linked list, right? Linked list really takes us into building more complex data structures. Because on a linked list, the basic data, think of the link or the car, that basic car, think about it like a node. It's called a node, it's referred to as a node, right? That train has data, people in there, right? The train has people, which is the value, right? So the node has a value, and it also has a chain. Maybe it's connected to another train, right? That connection there is a next pointer, right? Am I connected to something else? So how do I find out? I find out by seeing, does next have a value, right? So the node or the car of that train has two things that's important. The value, what is the value of that node? In that case there, on the first train, we see 12. And 12 is connected to another car. It's connected to 99. And that arrow we see there is our next value or our next pointer, right? So 12 is connected to 99, 99 is connected to 37, and 37 is not connected to anything. In that case, 37 is pointing to nil, right? So that's our basic structure we want to build today. We'll start off with a node. We'll start off with a node class. We'll define the node. the node will have a value, and the node will have a next pointer. The next pointer will be, the data type of that next pointer will be a next car, right? And I pointed to a next car. So the next data type will be a node data type as well. And our value, we don't care if we store numbers or strings in our car. It needs to be what? Any, or to make it more type safe, we're not gonna make it any, we'll make it type T. What's the terminology for that? Generic, right, Tiffany? So generic, right? So we'll make that linked list or that node a generic type. And we said with any, you brought up any, we said any is not type safe. Because any, then you could put in any object. You could mix objects basically. I could have strings, ints in the same structure. And with Swift being a type safe language, we want to type safe our node to say if I start off as 12, my next car, I don't want it to have some name, right? If I start off with 12, I want the whole thing to have numbers, right? So making that entire train have numbers makes it generic, right? But if it's a type any, I could have 12, I could have true, next car could have Julia, right? A next car could have random fellow, right? So those are the two differences there. Please write that down, the differences there. So any really is not type safe. Any is not type safe. Generic keeps your code type safe. Yes, sir?
Does that mean we shouldn't or can't apply a specific data type like string or integer, or is it better to apply generic so we can use it in library?
Back to when we did our stack data structure, right? When we instantiated it, we said let stack equal to stack angle bracket. We specified the type we want, right? So the minute you specify that type, it's a generic type, or in our case, we know the type we want, the whole stack becomes that type.
Right. So it's better to use generic.
Yes, yes, yes. If you're coming from JavaScript, you might want to use any, right? Just mix stuff into your array. But when you're taking out those any objects from your array, you have to cast it to everything you want, right? You have to cast it. Is this a Boolean? Can I do comparison there? Is this an integer? Can I add this to my other integer? Think of user defaults. User defaults is any, right? We see what we have to do with user defaults, right? Anytime we get back some value, we have to cast it to that value, right? Other than that, if I don't cast it, what type is it? Bienvenido. If I don't cast my user defaults value, I'm taking out, what type would it be? Any, right? So every time you're coming from that user defaults, you have to say, am I expecting a string? I'm expecting a Boolean. I'm expecting a URL. I'm expecting a date. That becomes a bit verbose there, right? As opposed to like knowing exactly what type you get it out. Cool? Very good. All right. So with that said, I think we should go to first draw the diagram. Everybody has a blank paper next to them. If you do not have paper, please raise your hand. When it comes to, we have paper here if you want paper.
Oh, that's okay.
It's not a pop quiz, sorry. Yulia is sweating. You are ready for your pop quiz? Okay, maybe tomorrow. Okay. I really, really want to emphasize, when you're building data structures, please draw the thing out, right? Draw it out. Even when you get to that interview and they tell you, oh, given some linked list, do some operation. Show the interviewer you're drawing the linked list and you're using pointers or you're using arrows to do what you're trying to achieve. Don't jump directly into code when you're dealing with data structures, right? Draw it out. You see the way we have this diagram here? Draw the thing out. Right? How am I going to get to 99 from 12? Right? I need to first be at 12. And then I walk to 99. And then I walk to 37. The interviewer sees your diagram. That's point right there. As opposed to directly jumping into the code. Right? Diagram the thing before you start writing code or even pseudocode. Draw it out. Talk about what you're trying to achieve. And then pseudocode. Then go to code. Because if you have a bug, you could go back to your diagram. What step am I missing, right? For example, if I want to remove 99, how do I remove 99, right? I gotta first see 12 and take 12's pointer, the arrow, remove 99, but first connect 12 to 37 in order for me to remove 99. So drawing it out first will help. It will always help. Cool? All right, so we'll do just that. We'll go draw our node object. We all have a pen, right? Everybody has a pen? Okay. So we'll first start off with a node. What's the two properties we say a node has or our car has? Yes?
Oh, value and a connection.
A value and a connection. Very good. So here we have a value and a connection. Awesome.
The connection is
The pointer, right? The connection is the pointer. The connection is that pointer to the next value. So here, connection is a pointer to the next value. Right? And the value is the actual value of that node, right? Whether it be 12 in our case, or whether it be a named train, right? The value is the thing you're storing. The people in our train, that's the value. Awesome. So we'll start off, we'll do our diagram here. We'll say this is our node. We'll use our train example. What's the first value?
7. Can I just give it any value or you have to?
We'll just use that same option we have here. So our first value is 12, correct? So we define that the value is 12. So value here is 12. Okay. Assuming our train only has one car for now, where is my arrow pointing? If you look at the last car in the lesson, where is my arrow pointing? To nil, right? So my arrow, as Amini is saying here, 12 will be pointing to nil, if that's the only car, right? So here 12 is pointing to nil. So that here is our basic node that will create our linked list. And the linked list is a series of nodes, right? So this is our node here. And with linked lists, with trees, with graphs, you always start with some node, right? So the node here is fundamental to abstract data structures. All right. So let's go code out our node. Let's go to Xcode, open up a playgrounds. You could call your playgrounds linked list. And that playgrounds, you'll be pushing it to GitHub, right? Yes? At the end, right? All right, so let's start off here. So implementing node structure. We'll start off with a class. We'll call it node. And that's our node, right? That's our basic node. It doesn't have any data yet. It's just a basic node. What did we say? We said we wanted our node to be generic, right? We want our node to be generic because our node doesn't have to be tied to one specific data type. Because if I come here and I say value of variable value is of type int, let's just give it some value for now, then that means every time I create a node, I have to specify what value it is. I have to create multiple node classes. Because this node only works with integers, correct? Right? What if my node, I want to work it with strings? Then I have to go back and refactor the code or whatever I have to do, change it to a string, or duplicate code, write the next class called node string, node int, node double, node float, node fellow, right? We see where we're going with that? We don't want to do that. So how can we change that code to make it work with a generic type? Right? What is the syntax for that? Back in our stack back in our stack class, right, what's the syntax do we? T, right? There's a T somewhere. We could name it anything. It doesn't have to be T, right? But we'll have some type T. But what's the syntax for it? Yulia is pointing angle, right? Angle bracket, right? Minnie says angle bracket. So right after our node name here, we'll put in an open angle bracket, close angle bracket. And here we're saying on line 5, our class node is a generic type of T. Again, it could be T, it could be A, G, whatever it is. Here, by convention, T you'll see being used everywhere. You'll also see element being used too. So now our value is of type T. We'll remove this 0 here, and we'll go on. I'm getting an error. Why am I getting this error? It's not initialized, right? Value T doesn't have a value. I'm in a class, I need to give this a value. I'm not in a struct. By default, a struct has a member-wise initializer. Our node class doesn't have an initializer, so we have to give it an initializer. Let's go ahead and give it an initializer. So we'll say init here. We'll say value is of type T. And here we'll say self.value equal to T.
If we didn't put the
Equal to value, sorry.
if we didn't put the underscore value and just put value, would it not?
Then you have to, when the person is calling it, they have to specify the label. Right? So when I create a node, I would have to say value colon the value, saying underscore.
Would it just populate on its own though? Like if you press, like, once you put it in, if it's not there, wouldn't it just kind of like, you just press the fix button and then just give you the name?
Yeah, when you're using it, it will automatically give it to you. In the when we start testing our node out, it would give it to you, right? But here we avoiding writing value in our function. It will be node open parens and then whatever the value is.
Right.
Yes, sir. The font bigger. How are we doing in the back? Is that good? All right, cool. Thank you, sir. Okay, what else did we say our node has? The next value, right? So here Jahid says we need a next variable. Oscar said it was connection, but here we'll call it next. What data type should next be? A node, right? Very good. So next is pointing to another node, right? So next is a node, which is optional. Right? Do I have to set the next value in my initializer?
No,
Why?
so it's an optional,
So what's the value of it?
optional.
Nil, right? It has a value of nil. So at this point, we are done with our basic definition of a node. So exactly what we had in our drawing here, that's what we defined. We defined some node that has a value, and it has a next pointer to a next node if it exists. In our case here, the node does not exist. Perfect. Let's test our node out. So in our train model, I'll actually just say train here. So train, we'll start off by defining a node of type. If we dealing with numbers, we'll say int here with our train. So we'll say type int. And it needs a value. We'll pass in 12. So our train started off, our train has one node, our train has a node or a car, and that car has a value of 12. Right? One node, one value, it doesn't point to anything, it's pointing to nothing, it's pointing to nil. Any questions about that? Any questions about our class definition, initializer, our syntax on 13? And this is very similar to what built-in Swift type uses those angle brackets with that signature? A set, right? Arrays are also generic. You could also do arrays like this, but convention, you use square brackets with arrays because an array is also a generic type. An array is a generic type, a dictionary is a generic type. So you've been using generics since Unit 1. Great. So now we want to go ahead, we want to connect our train to train 99. So I'll actually just say car here. Let's just say car 12. And here we'll say car 99. Car 99, we'll create the next node here. Value 99. Okay, so right now our train has 2 cars. We have enough information to link them up. So those are instantiating cars or instantiating nodes. Node instances. And here we'll link or connect our nodes. Or we could say link. We'll link our nodes. So let's link our nodes. We link car 12 to car 99. What are we using to link car 12 to car 99? Next, right? So we'll be using the next pointer or the next variable to connect 12 to 99. Let's go ahead and do that. So we'll start off with car 12. We'll say next. And this guy equals to car 99. So at this point, car 12 is connected to car 99. Now we want to print the result of our train. Like, what is the train now? So let's go ahead, print the current state of the link node. We'll say print car 12, because car 12 is the first one, so we print the first one, and we expect to see the next value. We'll go ahead and we'll run our playgrounds. Right? The result we were expecting in our console, we're expecting to see 12, some sort of thing like this, right? That might be easier for us to read, right? Right now we have some LLDB expression here, which doesn't quite add up to what we expect the result to be, right, everybody? When I have an array, if I have an array and I print my array, for example, if I have some array here, just call it fellows. We have an array of fellows, strings, and I say print fellows. I run my playgrounds. I see some array of fellows, right, everybody? Right? I see something that's readable, human readable. I see a Minnie, I see Lilia. But with our linked list, we don't have that because we created that structure from scratch, right? Our class here, our class node doesn't have any way to print itself, right? It doesn't have a way to print itself. By default, an array could print its contents on line 24. An array could print its contents because it has a description, right? So the array, the fellows, has a description. So when I say print fellows, it will print open square bracket, a Minnie, the contents of that array, right? That's already given to us from Swift. But now we have to take an extra step and provide a protocol so that our method, when the print method gets called, it prints some sort of description of what the content is. Anybody want to tell us what protocol we need to use there? What protocol can I use that overrides description? Yes, sir.
I think isn't it equatable?
Equatable equates objects, right? So if I want to find out if car 12 equal to car 99, I would use equatable. Very good. We'll come there later when we're trying to find out if the things are equal, but not equatable for now, but later we'll be using equatable, right? What other protocols have you seen that has description on it? Yes, sir.
I think custom string convertible.
Okay, why would you say custom string convertible?
Doesn't that provide like a textual representation
Of an object, right? Very good. So Benvenido says use custom string convertible protocol. Custom string convertible protocol has one property on it, description. Description, the minute you implement description, you could put in any print statement you want in that description variable. And when you say print my object, whatever customized print you have in that description will get printed out, right? So the big protocol we're after here is custom string convertible, okay? So let's go ahead and implement it here. So implementing custom string convertible to customize description of a node. We'll implement that protocol via an extension on our node class. So we'll use an extension like we've been using extensions in our view controllers, but this time I'm extending the node and I'm conforming to custom string. I'm conforming to custom string convertible. And as Benvenido says, it will customize the print statement for us. When we say print car 12, we could say how we want the print statement to look by overriding the description here. So custom string convertible. At this point, we are conforming to, or we're saying we're conforming to custom string convertible, right? We have to implement description. So start typing in description here and press enter. So type in description and press enter when description comes up. And this will be a computed property. A computed property meaning we need to return some value. In that case, what value are we returning? What data type? We return a string, right? So whatever we compute here needs to be a string. So to silence the compiler for now, we could simply say return empty string, right? But now we need to go ahead and write some logic of the outcome of our print statement should be something similar to this. If I have two nodes, it prints out the value of the first node, followed by an arrow, followed by the second value, or whatever other values, right? So it's value, arrow, value, and so on. Everybody? Right? So this is where we want to get to in our description variable here. So what do we want to do? First, we'll check. We'll use a guard statement here to see if the next car has a value. I'll return empty string, and I'll also return empty string here for now. And we'll talk about what's happening on line 16. So line 16 is using an optional binding, guard statement, optional binding. If there's a value in that next variable, it stores that value in our next variable right here, in our constant, right? If there's a value here, it stores it in our next constant value. If there's not a value, that means our car is pointing to nil. So if our car is pointing to nil, our statement should look like this. So we started off with 8, right? Or 12, sorry. We started off with 12. So if 12 doesn't have anything, we want our output to be 12, arrow, nil. So this is what we want. So if this is the occurrence here, we'll simply use string interpolation, and we'll say value is pointing to nil, right? So if I come to line 17, that means I do not have a connected car. It's only myself. I do not have a connected car. If I do not have a connected car, then value is 12 in that case. It's pointing to nil, right? It's not connected to a car. We'll come down to line 19 if we have more cars. So if we have connected nodes, Here we do not have connected nodes. We only have one node. On line 17, we have one node. On line 19, we have multiple nodes. So if we have multiple nodes, we simply say, go ahead, print the value, and go ahead and print that node, that next node. And the power of our description, now next knows how to print itself. Everybody? It's almost like recursive in a sense, right? Because here, next is a node, correct? A node knows how to print itself. So then it will just keep printing until it gets to nil. Any questions about that here? The last part. Oh, line 20, about explaining line 20. Okay, so value is just the value of the node, correct? And then when I get to next, right, next itself will be able to print what the value of next is, right? For example, 12 is connected to 99. If 99 is connected to something, it will call itself, right, to print itself, and it's connected to something. So it becomes kind of recursive, right, until it gets to nil, until it gets to line 17. There's no more connected cars. Yes, sir?
I assume that's property with nodes?
What's that?
I assume that's property with nodes?
It's not a property of nodes, it's basically the way we wrote this description here. If I say print 12, right now 12 is connected to 7, correct? So it will print 12, it will get to 7, it will also print 7.
And it'll do that again?
Exactly. Until there's no more anything to print. Cool? Very good. Let's go ahead and test this out. Actually, we could just run it and it should all just magically work, right? Run, and it should just magically work, right?
When it gets to next, does it read next? I mean, when it gets to next, does it read next as
Okay, so we got to, let's go back to, so we got to 12. Does 12 have a next value? It does. It gets to 99. Does 99 have a next value? No, so it just prints nil, and it's done.
So when it gets to 99, 99 becomes the value?
Yeah, exactly. It's always printing the current value in that case, right? Very good. Yes, go ahead.
So to print all the linked lists, we just type in first node.
Yeah, Yulia's question was, if I want to print out my entire train the way it is now, I start off with the first train, the first car.
What if you want to print just in first node?
The way the first node is, it will print all. I mean, you have to probably write a while loop and say first node, or we could write a first on it. When we write our full linked list implementation, you could just get back the first node, right? So, to review, what we just built is a node class, right? It's not a full linked list implementation. Everybody with me? As we see here, what are we doing? To implement or to add nodes, we have to go ahead and say node next equal to, node next equal to. Everybody with me? So I build it the way I want to build it. But most times you will see implementations like this on a code challenge, like given this linked list, or given this, given this linked list, go ahead and solve some problem, right? Linked list, the linked list we built here is referred to as a singly linked list. I'll put it right here. This is a singly linked list. Basically, a singly linked list, the definition of it is I could only see my next pointer, right? A singly linked list, I could only see my next pointer. As opposed to a doubly linked list. In a doubly linked list, I'll just put var previous here, and I'll put node here, and I'll say doubly linked list, and we need a colon here. So this would be a doubly linked list. If I could see my next car, and I could also see the car before me, right? So this is doubly, I could go both ways, right? Linked list, singly linked list, I could only go forward, right? So I start from 12, I go 99, and then I go 37, right? So 12, 99, 37. In a doubly linked list, I could go from 12 to 99 back to 12, right? Because I have pointers in both directions. Everybody? Cool. All right. I think we'll take a short break here because we have enough content. I don't want to go too much too quickly. But first, the first thing we just built here is a node class. So we implemented a node structure. We'll say abstract data structure here. And we connected our nodes, instantiated node instances, and linked our nodes. I'll even say linked list here. Linked list using connected nodes. And we were able to print it, and the magic of that whole print statement, we had to go ahead and conform. We had to conform in order to print our car. In order to print our connected nodes in a readable manner, we conformed to custom string convertible. Right? And in the custom string convertible, we implemented the description. So we implemented var description and wrote the print logic.
Description comes with it?
Yes.
Oh, so you didn't type out
No,
description.
it comes with it. The minute you say you had a compiler error, right? It says doesn't conform to custom. Exactly, exactly, exactly. And we show the differences here because fellows just comes with it automatically. It comes with description automatically. I have fellows.
Because it's a string, so it automatically comes with
An array. The arrays know how to print the contents.
okay. So even if it was a random numbers, it was still
Exactly, it would still print, right?
Well, obviously, I know that.
Yeah,
That's
no, that's fine. No question is too small. All right, cool. Any questions? All right, so let's take.
If it was a doubling, how would you initiate the previous?
You would do the same manual previous here. So I would say car.next is car 99, and car 99's previous is car 12.
It would be car
So
99
it would be like, it would be car 99 dot previous equal to car 12.
We have to make another print statement if we wanted to do like a doubly print.
Yeah, you'd have to do another print statement.
Would that print statement have a back arrow or just
You could have like a tool, like you could have an arrow like this. You know? Right? Does that make sense? So it goes both ways. Cool. All right, so we'll take a break here. We'll come back at 11 to continue. We'll come back at